Our next speaker is Mike Hinman from Sherwin-Williams. Mike is currently the Protective and Marine North American Technical Director for the Sherwin-Williams Company, where he has worked for over 15 years. He has a BS in Biochemistry with a minor in Germanic Studies from Indiana University. Today, Mike is going to highlight the potential of optically activated pigment coating systems as in-process time savings opportunities for railcar lining applications.
Thanks, Jim. So as Jim said, thanks everybody for coming, by the way. As Jim said, I'm Mike Hinman from the Sherwin-Williams Company, and I'm going to talk to you a little bit today about a coating technology that can make any post-application inspection process go a little more efficiently. That technology is referred to as optically active pigmentation, or OAP for short, so in the rest of the presentation I'll refer to it as OAP. And it can significantly improve your ability, your efficiency in delivering high-quality lining finishes. So first, let's talk a little bit about what does it look like physically. As you can see on the screen, it's a light yellowish powder, a fluffy powder consistency, not unlike talcum powder. But what's far more impressive is what it actually does when you formulate it into a coating. It possesses the ability to luminesce, so that's just kind of a fancy way of saying if I shine the right light on it, I get it to glow a certain way, and that can tell me certain things, right? So let's talk a little bit about what luminescence is. Before we get into the graphic up on the screen, I thought maybe I would share with you some anecdotal kind of things that might get you thinking a little bit in the right direction in terms of what we're talking about. And so as a formulator, we're concerned with two aspects of luminescence. One is fluorescence and the other is phosphorescence. So for an example of fluorescence, think back to when you were like, and I'm not sure how old all you guys are, but think back to when you were in high school and you first got into Led Zeppelin and you're begging your mom and dad for that Led Zeppelin black light poster with the black light, right? So that effect that you were going for to see them up there in those cool glowing colors, that's fluorescence. So phosphorescence, a good example of that, and then again, I don't know where you guys are from. I'm from Southern Indiana, and when I was a kid in the summertime, we used to chase fireflies. We called them lightning bugs, chase them around, just so we could, for hours, catch them in a jar and just be amazed by that effect and all those cool colors. So that's a good example of phosphorescence. If we could get just a little bit into the science behind it, just what I've got on the screen here is the nucleus of an atom, and those kind of Wi-Fi looking bands are intended to represent electron shells. So things that fluoresce have electrons in lower shells that when they absorb light energy, like so, kick up into higher levels. So in this transition is what your eye sees as kind of a blue tinged glow, if you will. So that's fleeting for fluorescence, though. When you remove the light source, that electron emits photons and drops back down immediately to its original ground state energy level. So again, what you're seeing when it fluorescence is this transition right here. You take the light source away, immediately the fluorescence effect goes away. By contrast, phosphorescence, same concept, except when it absorbs the UV light, things that phosphoresce contain electrons and shells that kick up even higher. And it takes a significantly longer period of time, on the order of hours, for those electrons to go back to their ground state. So what that translates to is remove the light source from something that phosphoresces, and now you have an afterglow. So that afterglow is not necessarily something that's advantageous to be included for a coating. So what we focus on as formulators is those things that fluoresce. This is a good example of a single coat application, meaning that the top coat contains the OAP pigment. This is an example taken from a marine tank lining demonstration that was done several years ago, and this slide has been used in many discussions about the value of OAP because it's a pretty good example of what it does. So first of all, you can see across the whole screen it's fluorescing. Now it's having a blue light shine directly on it. The entire coating is fluorescing. And it's significant because you can see complex geometry, which is the idea behind using OAP to begin with, is so when I have complex geometries and I have areas that can result in deficient film or holidays or pinholes, now I can maybe have something that allows me to see those more quickly. So you see the complex geometry along the weld seams there, and you can actually see that in this particular application, you've got 3 pinholes that are fairly visible. So imagine you can walk into a room after something you've just painted, turn a light on, and have all your defects show up immediately. So now it's in the wet, and I can actually do something about it more readily. And by the way, when we're talking single coat application, you can see that the defects show up as dark. So the top coat is fluorescing, the defects will show up dark. So in this example, single coat application is fine, right? So we just saw an example of how that works, but in the protective world, we don't often have the luxury of only using a single coating. So we use multi-coat systems to protect our assets. So how do we utilize OAP then in a 2-coat system? Well, what we do is we put the OAP in the prime coat, and we use a non-OAP containing top coat. And when we are doing our post-inspection, our post-application inspection, what we'll see is those defects now, instead of appearing dark as they would in a single coat application, they will actually fluoresce through the top coat. So you can see that here on the edge of this particular coating, that blue that's coming through the top coat is an area of insufficient film on that edge. So you've got OAP in the prime coat, and it's fluorescing through the top coat. Both halves of those panel are the same, just one viewed under the blue light. Inspection benefits. Let's talk a little bit about the light source. So a traditional white light inspection, which is something that you're going to have to wait for the duration of a cure schedule to do typically anyway, is going to often result in gloss interference or glare from the light that's being shined and shadowing, which makes the whole point of OAP a little more difficult in that instance. It makes it difficult to pick up those defects. And so if you remember, if you go back and look at the blue light slide, this is the same level of intensity, if you will, from the blue light being shined on the surface, but you don't see the glare effects that plague the white light inspection. And certainly when we factor in the mechanical, electrical methods that are required to measure for holidays, that certainly require cure schedules to be observed. This is obviously much quicker. You can do the inspection in the wet with the blue light and be that much further ahead. So in the upper right-hand corner, you see the glare and the shadowing. In the lower left-hand corner, you can see an area that would have benefited probably from the application of a coating that contained OAP. What you've got there is surface rust that is coming through due to insufficient film build coverage on that particular area. So certainly OAP could have benefited that situation. So we've talked about what OAP is, what it looks like, what it does, how it can make your inspection process a little more efficient. Let's talk a little bit about safety. In order to consider the safety aspects of using this, it's not just the OAP technology itself, it's the inspection tool. So how safe is that white light? To do so, let's consider both ends of the light spectrum. So on one end, you've got safe, visible light. On the other end, you've got harmful UV light. And right in the middle between the two is blue light. So inspecting something that fluoresces with a black light is something you could do, but again, it emits that harmful UV light. So with the advent of LED technology, now we have the ability to kind of harness blue light, if you will. So gone is the need to use a filament bulb UV light to do this inspection. We can use our handy LED blue light to do the same inspection. And that blue light that is emitted by that inspection tool is no more dangerous than the blue light that comes from your computer screen or from your TVs at home. And as I'm sure you're aware, there is eye protection that you can use to filter out that blue light for those everyday applications. So certainly in an industrial application, there are going to be recommendations for eyewear to use as well. So NACE RP0188 is the reference that kind of gives some guidance on how to do that mechanical measurement. ASTM E2501 is essentially a reference that says I can do the same thing if I use OAP, I have a blue light source for inspection, and I have the right eye protection. I also wanted to talk a little bit about water and food safety. So when it comes to water safety for NSF, there are NSF standard 61 versions of OAP coatings that exist today. Those are for 1,000-gallon certification, and the implication is here that you can actually, they're safe potentially for use on other size tanks. You just need to do the testing to confirm that, right? As far as the FDA is concerned, they've approved the use of the chemistry in general. What that implies is that I don't need to be concerned whether I'm using something that contains OAP or not. I don't need to be concerned that the OAP content is going to impact my results. So I've got to do the testing anyway. It's okay to use something, to start with something that has OAP technology in it to make sure that it's okay. So that takes care of the safety aspect. We know what it does and how it's used, and a little bit about the safety. I thought I'd give you a little bit of insight to the formulator's perspective on this. So there are organic and inorganic OAP pigments. So how do we decide which ones we want to formulate with? How does the technology best serve us in terms of better helping to serve our customers? So first and foremost, organic OAPs are cheaper than inorganic. So that gives them a leg up right there. And actually, you'll notice that in all these categories, organics are going to win in a landslide. So I've got something that's, my cheaper option is organics. With organics, I also get varieties that are more efficient. So I can use less to get the same effect. So now I'm using less of a less expensive thing. That's probably where I'm going to need to go. When we talk about luminescence, I'm relegated to blue fluorescence with organics, as we've been talking about. So if I wanted to be able to tailor the color of that phosphorescence a little better, I could use inorganics, which phosphoresce. But remember, we talked about the limitations of phosphorescence being afterglow. We don't necessarily want to use those in coatings. So again, points to organic. And then as far as incorporation into a coating, the solubility parameters of the organics are such that they're more easily incorporated than the inorganics are. So now my manufacturing partners, when I bring my fancy new technology to them, they're going to be a little more excited about jumping on board with me and making these things work. So we've talked about whether to use I know I'm using organics, right? And I know how these things work, but you might be saying to yourself, okay, I've heard some reference to tank linings with this stuff, so why, if this stuff is so great, why is it only limited to tank linings? Why can't we use it in other applications? There are actually a couple of really good reasons that that's the case. OAP pigments are not light fast, so prolonged exposure to UV light will render them ineffective. The other and slightly less important reason is because my color palette is limited for two reasons. One, in a single coat application, I'm going to want as much contrast between the things that fluoresce and the things that don't fluoresce as possible. That's going to happen with a lighter coating. And in a two-coat system, I also am not going to want to have too much of the OAP in there. I'm not going to be able to create black, right, because the pigment itself imparts some color to the coating. But not to fear. So that kind of eliminates atmospheric coatings from being a prime application right off the top. But not to fear. OAPs they have good broad spectrum chemical resistance. So now I don't have to be worried about if I'm using these in a coating, I'm going to compromise my ability to pass what I need to pass depending on whatever commodity I'm having tested for service. So that makes tank linings a perfect fit. So in effect, that concludes my presentation. Thank you for listening. OAPs, good for use in tank linings, good for allowing you to detect defects more efficiently and decide what you want to do about them and repair it in process. That's about all I have. I'll take any questions. Anybody has?
Yeah, you
Yes.
showed a slide of the eyeglasses. Do those help or hurt the ability to see the variances in the coating? You know, because there were different colored eyewear, I just wondered if there's an issue there or not.
Sure. In theory, no. I mean, I suppose if you're using any form of eye protection that alters what you're looking at, there's going to be some change. But in theory, no, it does not impact negatively the ability to see the defect itself.
Well, thanks, Mike. We appreciate your work here.